name is Simon, and I'm from the University of Southern Denmark at the SGU Center for EnergyInformatics, and today I'm going to present the paper Geometry-Driven Automatic Placement of IoT Sensors in Digital Twins for Smart Building Energy Management. So this talk is going to be a bit different from the others, since this is deep dive into 3D and the geometry and analysis of it. So our contribution claim is that with simple geometric steps for classification of interior and exterior walls and window and door openings for 3D models, then the sensor can actually be placed with a corresponding rule to achieve the correct sensor placement in the 3D environment. So I want to show a bit of a demonstration of the method that we propose in this paper. So you see here we have a demonstration building where we select a specific floor that you can see that flashes in red here. The building itself has two openings, and if we zoom in a bit more, we compute a centroid in the center of the rooms where we also cast rays from towards the walls vertices or the floor meshes. And then the red lines denote that's an interior wall because it has multiple hits on walls in other rooms and the room itself. And the green ones denote an exterior wall because there's only a single hit when we do ray casting towards the wall. So if we continue the animation a bit, zoom in a bit more from a different angle, in the same step we also did vertical probings from the floor mesh itself, and we also did wall segments so we can see which wall is the longest and on what side of the opening it is. So vertical ray probing, we find voids from the floor mesh perimeter, and as you can see we've already placed, for example, a door sensor in the 3D environment, even though the scale it's just scaled up a bit for demonstration purposes. But the window sensor or the door sensor itself has been placed at a rule with about 80% of the height of the room. Even though there's no room here, the height can be inferred by vertical raycast. So it's 80% up on the room and a little bit to the left of the void at the door. And then the CO2 sensor on the right is placed on the largest wall segment at the interior wall. So the key idea is that we can, by the geometry itself, we can identify interior and exterior walls. We can classify window and door openings by the visible voids, or you could actually tune it to different materials and filter for that. If that is in your scene or in your 3D environment, we use room centroid, the boundaries of the floor, and the height can be inferred by raycasting from the centroid itself towards the ceiling, or towards the roof. And we use the idea that real-world sensor placement rules are inherently geometric, or at least a lot of them are. So why does this work better? So digital twins rely on correct spatial alignment of sensors in order to give the correct impression, the correct analytics, and the correct maintenance that might be needed. And doing this process manually is very slow, so aligning sensors is very slow in 3D. It can be very error-prone and simply doesn't scale if you have to instrument a lot of sensors and align them. So poor placement leads to wrong analytics, diagnostics, and poor insights. So there's a need for automated model-agnostic and scalable placement. And we see the primary use cases of this paper as either to make a digital mirror of the physical installation or as a planning tool for sensor placement before installation. So why can't we use BIM metadata or IFC? So what we see out in the industry usually is that the BIM metadata is simply missing or is inconsistent or removed when we're exporting to more flexible formats, for example GLTF or GLB. And many retrofits lack IFC entirely, so there's no model at all. And existing systems rely on manual annotation, which is very common. So we want something that's automatic and reproducible in many 3D models. So we also looked at current literature. So for example, we looked at metadata-based placements. Usually these are very academic literature because they have very feature-rich IFC, which we haven't seen that much out in the real world. We also have deep learning AI models, which are very heavy, and we kind of want a lightweight and more deployable way for embedded environments or browsers. So we see that there's a gap for geometry-only automatic placement methods. So the overview of the method itself is pretty simple. We select a floor or a room that we want to identify, and then we take the meshes for each of these or for that specific room. Then we compute a centroid and calculate the height with raycasts, and we detect inner and outer walls with raycast towards the floors or the floor mesh for for that specific room's vertices. We do detecting and window openings with vertical probing along the perimeter of the room or in the walls. And then we apply the sensor-specific placement rule. The only input that should be is the model itself, exported from maybe a BIM or similar. And the output should be automatically placed sensors ready for digital twin visualization. Step 1, we identify a room. Step 2, we compute the centroid from the average position of all the vertices from the floor mesh. Classify wall boundaries, just it's the same as from the demonstration. And then with vertical probing, here you can see a bit better maybe, that we shoot up vertical rays from the floor for the perimeter of the floor towards the ceiling. Then we can classify opening based on when the hit actually starts and stops. Then we lastly apply the specific sensor rules. For example, for a CO2 sensor, it's usually on the inner wall and about 1.5 meters, 1.6 meters on the wall, or maybe a smart thermostat. So in most buildings, it will be on the inner wall at human height. But of course, these parameters can be tuned to specific buildings. So before I go into the case study, the implementation itself runs in the browser in a three.js environment. And it does real-time placement and visualizations with no backend strictly required. So it uses also the building model without any pre-processing at all. So the case study was conducted at the Mask 1 building at the SDU campus in Odense, Denmark. And as you can see here on the bottom left, we have 330 devices collecting over 4,200 data points. So doing the manual alignment would take a pretty long time. So what I should state is that the 3D module that you see here was actually done after instrumenting the buildings with sensors. So we had to use the 3D module as a digital mirror from the physical installation. Here is the floor plan. We see that there's a very regular and consistent office rooms. They're very, very similar, so it's pretty easy building to conduct a case study in. And just for fun, we did the 3D models. We also instrumented the sensors via an app where we scanned QR codes and scanned sensors on the back in order to associate it to that specific floor. So that's some small metadata that we actually had in our case, but it's not strictly needed for the methodology itself. And then for more hinting in the metadata, we actually have window and door none tags for the sensors themselves, just to hint at where the placement should be, but this is not strictly necessary for the method to apply. So applying the method, we see here on the left a real image from the building itself, and on the right we see how it corresponds in the 3D world. So it's very, very close. It's just that the smart thermostat, we did a little bit of we set it at around 20% height on the inner wall. On the other side of the same office, we see the left here in real life, where we have two window sensors and one smart thermostat, and it correlates pretty closely to 3D world. So very nice. So a parallel project we are working on is creating a full twin, or at least a digital shadow, of the entire SDU campus. So imagine when we have to fit all and align all kind of sensors or other resources in this 3D world. It will take a long time. So we're going to utilize as many automatic tools as possible over these 200,000 square kilometers. Or square meters, sorry. Yeah. So it's not a silver bullet approach, because there are some places it fails. So for example, we have here in the main entrance from the same building you saw before, the Mask 1 building, the atrium spanning the entrance area of the first floor. It faulty classifies the inner and outer walls because there's simply too much open space, and the geometry is pretty irregular. So it doesn't really work here. So here we need to do manual alignment or use other methods described in the literature. So results. Just to recap, it worked for all regular office rooms, and where the digital placement matched the real-world installation, and it failed for highly regular spaces. The limitations again, multi-level voids are very hard to do with this specific methods, and rooms or floor meshes with heavy concavity or disconnected volumes are almost impossible to do. And the limitation is also that we need manual input rules for specific buildings that have a specific layout, but maybe we can create a catalog of this and then make it more automatic, or at least more more easy to do, more simple. So for future work, we might work with a hybrid approach. This is one we see as the most feasible. So small hinting, for example, only metadata tagging the doors, so we can have better anchor pointing and better alignment with sensors. So hybrid approach between metadata and geometry. For lightweight semantic hinting. So conclusion is that the geometry alone is enough for a plausible and reproducible sensor placement in regular indoor environments, enabling both digital mirror, as we saw in the case study, or use it as a pre-installation planning tool before you actually instrument sensors at all, without reliance on IFC or other metadata or manual annotations in the 3D model. So thank you very much. My name is Simon. You can contact me if you have any questions.